Thank you very much, Jingfeng, Guiling, and others for giving me this opportunity to present at this star-studded symposium in honor of the greatest star of them all, Professor Rafael Bras. So this first slide has my mandatory affiliations and funding organizations. So the first part of this two-part talk will focus on my work in general, what I've been doing since my PhD with Rafael. So overall, the work that I do is, I call it adaptation to a changing climate adaptation, but civil and environmental engineering sciences in the service of climate adaptation. Here are some of our journal papers and some of the areas which they intersect. So besides some of the quotes and highlights in Nature Science and PNAS, the journals, as you'll see, are mostly concentrated in hydrology and meteorology, which reflects my PhD background, and there is a lot in transportation by now, which possibly reflects my civil engineering background. But then there are several others, from communications biology to communications physics, from ecology to marine sciences, policy, finance, and law. So one question that I have been asked is the following. Are you a civil and environmental engineer? Which disciplines make this civil? Which disciplines make this uncivil? I'm just mentioning that for the fun of it here, but for early career researchers, especially, this kind of questions do come up and they're incredibly important. Here, personally, I think these are ill-posed questions, but let me move on. So one other area that I work on very strongly is broadly in data sciences, big data, small data. So when we think about machine learning and AI these days, we talk about generative AI, computer vision, deep learning, etc. But in our fields and in many other fields, we also work with extremes, which are rare by definition. So we do not have big data usually for extremes. And then we talk about small samples in many cases where we have to do correlation and causation. Plus, things these days are very much interconnected, so we often have to rely on network science. Once again, some of these questions, these are not exclusive to civil environmental engineering. In this case, what is AI, what is not AI comes up as well. And again, I think these questions are ill-posed. In terms of history of AI, here is somebody's version of AI history. There are many such versions. I just took one, I believe, from Medium. There is a citation here. But the idea here is when I started my PhD late 1990s and ended early 2000s, the paper that we published, this is jointly with Rafael Bras, Journal of Hydrometeorology, was in precipitation nowcasting using radar and numerical weather prediction models. And it used physics, statistics, and what would now be called machine learning or artificial neural networks. Fast forward early 2020s to now, so late 2024, this paper was published by my PhD student then and a data scientist, along with a couple of my former PhD students and stakeholders. And title is a bit different, but same problem: numerical weather prediction model outputs, radar information, precipitation nowcasting with physics, data, and machine learning or AI. The interesting insight here is that the state of the art of AI and machine learning has improved significantly by now. The state of our understanding of physics has evolved, has progressed, but not at the same pace. So if you look at the top left, instead of history of AI, now I call it a personal history of AI in the context of precipitation nowcasting. Moving on. So after that 2003 paper, and of course, we are not the only ones doing that work then, but there are other groups such as the group led by Anna Barros, who are working on physics and AI in the context of precipitation nowcasting, as were we, and there were a few other groups, but the field has not progressed or did not progress significantly as far as I could see until there was this interesting paper by Google DeepMind in 2021. This was in Nature, Mother Nature, and this was called DGMR, Deep Generative Models of Radar. They claimed that it outperformed the state of the art, but it did not do a good job for extremes. On the other hand, in 2023, a couple of years after, there was another paper also in Nature, Mother Nature by Xinhua and UC Berkeley called Nowcastnet, where they used physics. They said this outperformed DGMR and it performed better for extremes. So extremes are rare events, not as much data. So what happens? How can we predict those with machine learning? Well, if this particular sample, if you will, both of these papers representing one sample, if we go with that, then the one difference was on the left, Google said this is physics free. And on the right, Xinhua and UC Berkeley said it's physics conditional. And that improved significantly when it came to extremes. However, both of these were untested for hydrology, and that's what we did in terms of looking at HRRR with ground truth, Nowcastnet, and persistence. And what we found, this was project funded by NASA. The stakeholder was Tennessee Valley Authority, and we found this is that earlier work that I mentioned. We found that we can improve with hybrid physics AI. TVA said this is one of their most critical challenges. In fact, they gave us very good testimony, and they are actually testing our implementation and metrics on their operational system for river forecast system right now. All right, in terms of entrepreneurship, going forward from research to entrepreneurship, and I define entrepreneurship both as community-based work and private sector entrepreneurship. So we have done some work for Climate Ready Boston. We continue to be engaged with them. We have done some work for communities such as Brookline, Massachusetts. We have done other work in this region and in fact around the world. And in this region, our work has gotten very good model support. So here is me and some of my colleagues with Mayor Michelle Wu of Boston on the left and Governor Maura Healey of Massachusetts on the right. In terms of private sector startups, here is our first startup. This was opened in 2016, sold off around 2021-ish. This is my PhD student, Evan Kodra. The company he launched was called RISQ, R-I-S-Q, RISQ as in quantifying risk. This was physics data method including machine learning, but not just machine learning. So physics data method in the context of urban climate risk. And this, the monetization pathway was through muni bonds or urban bond market. And this was sold to the Fortune 500 company that owns the New York Stock Exchange. That company is called Intercontinental Exchange. Ticker name, unfortunately, is ICE, but is the other ICE. And it was an incredible journey for my former PhD student, Evan. One of his first papers was highlighted in the journal Nature as a research highlight. And by the time he launched his company, this was highlighted in the Wall Street Journal. So amazing journey, and seeing this success, many others of my PhD students followed suit. So this company, Zeus AI, Zeus as in the Greek god is about weather AI, co-founded by TJ, Thomas Vendel, and Kate Duffy, both of whom were planning to be there at the AMS. I don't know if they eventually made it. And then here is Udit Bhatia, who is a former PhD student, now a faculty at one of the IITs, Indian Institute of Technology. His company is doing very well. It's in flood prediction and flood resilience. I'll come back to talk about it a bit. And then here is Enodia by Jack Watson on installation resilience. I've been involved in all of these, usually as co-founder, chief scientific advisor, in one case as an advisor. So 5 PhD students represented here with 4 startups. Most of them are in Greater Boston area. 1 is in India. So I'll now quickly breeze through some of our work in urban flooding and transportation resilience, how we go from research to product to community implementation. So some work we have done in the context of rainfall extremes and such, and physics-guided uncertainty to infer about watershed scale precipitation and flooding based on climate models. And some work we have also done in transportation resilience. So on the left, that's New York City MTA mass transit after Hurricane Sandy. And it shows that the total loss of revenue after Hurricane Sandy was $124 million, and half of that could have been saved by using some organizing principle. And we have also done some work along the Northeast Corridor and across the world in terms of metro systems. And recently, we have been focusing on urban flooding, urban hydrologic modeling to hydrodynamic modeling, fluvial, coastal compound flooding, leading to then understanding what it means for accessibility and resilience of multimodal transit systems, that's road and rail, what this means in terms of failure and recovery, and also trying to understand then what this means in terms of loss of accessibility, and not just overall loss of accessibility, but also what this means in terms of inequality of that accessibility, inequality in terms of total population, but also inequality in terms of population along with social vulnerability. In terms of product development, here is an SBIR on the left, Small Business Innovation Research, which is joined with a company called Kitware, where we are building some of these interactive dashboards with some interesting science underneath. And on the right, that's that company AI Rescue, where we are doing community implementation. These two case studies, one is in India's national capital region, one is in Kerala, India. And then this company is, I'm a co-founder here. Udit Bhatia, my former student, is the CEO and the primary person. And here we are going from his MIR lab, the science in his MIR lab, machine intelligence lab, all the way to AI Rescue, from the urban context to the physics-guided AI Rescue engine, dynamic risk, and leading on to decision support. With that, thank you very much.